Okay. So today we're going to be going over the exam, and then after the exam, we'll probably spend a little bit of time, depending how much time we take on the exam, to go around the room and just ask you where you were confused. I like to sample the class at about this point just to kind of see what you guys get and what you don't. The good news is, good news, bad news, really, we've gone very fast. So I've taught this class differently than I have previously, and we're like a week and a half ahead of schedule. What that means is I'm going to take a little bit of a breather, I'll slow us down for a minute, and then starting next week, we're going to jump into what we call sequential devices. So circuits that have memory. So we can build more complicated logic, right? One of the labs we'll do upcoming is building a garage door opener, right? It has to know where is it now so that it can decide when you push that button, do I go up or down, right? Circuits to remember. That's what we're going to start next week. It's a little bit intense. This week is going to be a little bit of just kind of bolstering the skills that we've built so far so that no one feels left behind. So for the exams, I said I was going to have them all graded by today. I do have them all marked today. I don't have them submitted. So I'm going to hand them back so you guys have something to reference as I go through, but I'm going to need to collect them again so that I can actually enter your exams in. Some of you, I haven't gone through and made sure that I didn't miss any yet. And if you took it online remotely, I haven't done that yet, unfortunately. So it'll be done soon. It would be done sooner. I bought a house and had a car stolen both like last week. So it's been a little crazy for me. I'm just going to go around. I know you took it online. What's your name?
Right. I took it online.
You took it online. Name. Great. All right. Name.
I was online.
Online.
Oh, Matthew Finger.
Name. Okay. Your Zachary, right? Yep. I know one person. Okay.
Brian. David.
Name.
Yeah.
Okay, so I'm going to need the exam. Those that just walked in, I'm going to need the exam back because I haven't entered the scores, but I have, I think, marked all of them. Okay, let me find my copy. All right. So overall, I was very, very happy with how this turned out. I thought this was a hard exam, and it turned out you guys did really well, really quite well. I don't have the distribution yet, so I don't know if it's going to be curved. The likely reason it gets curved is because it was a bit of a time crunch, and some of you just didn't have a chance to get to number 12, the last one, which I get. So if that ends up putting the average too low, I'll end up putting a curve on it, but I just don't know yet. Overall, the biggest mistake on this exam, and I'll point them out as they go, but every time I point out the biggest mistake, it's going to be that you guys didn't read directions. Other than that, you guys may have gotten 100% if you read all the directions. So on the first page, I would say everyone got all of the points, I think, on number 1. For the first 3 problems, the biggest mistake I saw was some people were inserting zeros in weird places that I haven't quite figured out why that happened yet. So like the answer on number 2 was 1, 1, 1, 1. Sorry. Really, there's 2 leading zeros on this, right? So 0, 0, 0, 0, 1, 1. 1, 1, 0, 1. But I think like 4 people put a 0 there. And I'm not quite sure where that came from, right? Because this was just text for 3D. And I don't know where the extra 0 kind of got slotted in. Same thing happened on number 3. There was often an extra 0 or an extra 1. I don't know if that was just people not able to line the ones up right and kind of got confused. Number 4, I would say nobody missed, I think. Number 6 got people a little bit right. This is just the 2's complement subtraction. And what we like about 2's complement subtraction is it's easy to turn into addition. So if we look at number 5A, I'll use as the example. That was your subtraction. We don't want to subtract that, but we know that it's a negative number minus another negative number, so it should get more positive. Now, one way that you can make sure you get this right is convert these both to decimal, right? Numbers that you recognize, do the subtraction, and then do the 2's complement subtraction and make sure you get the right thing. This was open internet. You could go and use a calculator to verify the number and then go back and show your work, right? So the first step that you would want to do is convert the subtraction into its complement, right? Because a minus becomes a positive. And the way we turn this from a negative to a positive is we flip all the bits and add 1. So that just becomes 0, 0, 1, 0, 0, 0. A lot of people miss that 0. 1, and it would be 0, but it becomes 1, 1 because I add that extra 1. And then I'm adding that to this, which I just copy over. And I go through and I add them. Right? That's 2's complement. It'll probably show up on the final, but you probably won't see it between now and the final, to be honest. Overall, I would say most people got really good scores on that first page. All right, page 2 caused you guys a little bit more difficulty. Let me draw that circuit up here. And as I go through, if you have questions, go ahead and shout them out so I know. And then we label this A, B, C, D. Okay. So what you want to do here for part A is come up with an expression for this circuit. Now this question, I want to make sure that you guys understand because this is coming back around, but more complicated later. Because right now you made the assumption that all of these gates react instantaneously, right? That's the easiest situation is there is no delay in these gates. Coming up, I'm going to be giving you these gates and telling you that there's a 3 nanosecond delay here, a 4 nanosecond delay here, a 10, right? I'm going to go through and give you delays, and you're going to have to figure out how that causes problems in the circuit. So if you don't understand this now, you're going to be in trouble later. So I'm going to go through this pretty thoroughly. So what you want to do, the reason I label these nodes and make you draw them out is make you think about what those nodes are doing. And it's true for both parts A and B. So on part A, when I write the expression, I'm going to go through A, B, C, and D and just write what they are and then combine them for F. So I say A is X or Y. And I say B is y XOR z, and I say c is simply not x. And then that leaves d equal to b or c, right? B or c, which is equal to, well, I just plug them in. Y XOR z, or not x. Now, f is just a XOR b. I'm sorry, a XOR d, which is equal to x or y is a. That sounds hard, right? X or y, not x or y. X or y, XOR d, which is and I'll just explicitly call that out, right? That's the expression. That's all you have to do to get A. Some of you did some really convoluted things that I had to go and like write out truth tables to figure out how you got to it because I couldn't follow along. I recommend doing it this way because you'll end up with it, especially when I don't say simplify, right? I didn't tell you to simplify this expression, so just give it to me. All right, so once you have that expression, we can go on to part B, which is drawing the timing diagram. So I'm going to take this board here and push you over a little bit. All right, squeeze that in here. Okay, and then X, Y, Z, A, C. All right, so I asked you to exhaustively test this circuit. What that means is I need you to test all possible input combinations. The easy way to do that is just to count up in binary for X, Y, and Z. Now, I like to use X as my least significant bit, the first one. Some of you flip that around, totally fine. It made grading harder, but I didn't specify, so no problems there. And so here I just said 0, 1, 0, 1, right? This is the same kind of thing as writing the truth table. Y then was 0, 0, 1, 1, 0. And I'm not going to finish. I'm just using what 6 instead of all 8. Then X was 4 zeros, 1, 2, 3, 4, and 4 ones. Okay. Once you've established that, if you did that, you got like 3 points. From here, you just want to worry about only these expressions. So A, what is A? X or Y. If you did anything else, some people wrote like A for B, like they swip them around, which is not correct. Make sure that you're drawing A, which is X or Y. So one way of doing this is going and looking at anywhere X or Y is 1, it's 1. So 1 here, 1 on both of these because of the Y, and then 1 over here for the X. Everywhere else is 0. A is X or Y. Same thing for B, but it's Y XOR Z. This one is a little bit harder to see, which is it's saying anytime they're not equal, right, then it's 1. If they are equal, it's 0, right? Because 0, 0 is 0, and 1, 1 is 0 in an XOR gate. Okay, so B, Y XOR Z, 0, 0, 0. still 0, 0, therefore 0. 1, 0, well, they're different. We like that. 1, 0, they're different. We like that. 0, 1, we like that. 0, 1, we also like that. And then we finish that out. C. C is not X. This was not X. Okay, it's just doing the inverse of what X is doing. If you did anything besides not X, you would have missed points. Some people did like not Z or something, which got confusing. I assume they just mixed up the circuit because it does look have that crossover. D, B, or C. So you could go back and try and figure out this whole expression, right? And look and say if it's, well, it's not X or Y, X or, well, that'd be hard. Why not just say D is equal to B or C? Well, now I just look at these two lines. Nothing else matters, as long as I did these two correct. And when I did your grading, that's all I looked at. So that if you had made mistakes previously, as long as you based it off of B or C, you were correct. Okay, so B or C is, I'm gonna do the same thing as I did with the OR gate up here, which is anytime one of them is 1, I'll give it a 1. Then lastly, F is also easy. It could be hard if you tried to use the full expression to figure it out, but don't do that. Do A, X, or D, right? So A, X, or D. So anytime A and D are different, I get a 1. So they're different at time 1. They're different at time 2. They're the same at time 3. Same at time 4. 0, 1, different at time 5. 1, 1, the same time 6, and so on. That's how you're going to deal with these circuits. It's just one row at a time. Get your input set up. So your X, Y's, and Z's, or A, B's, and C's, whatever your inputs are tend to be called. And then go back and through and fill them out, not worrying about the complicated expression, worry about the expression for the output of the gate. Everyone follow that? And some of you, if you kind of missed, you probably noticed that I did do this to remind myself. I went back and wrote equals B or C is equal to A, X, or D, to remind myself that that's what it was supposed to be. And so I did try and grade it that if you made a mistake somewhere earlier, it didn't cascade into a massive errors, because I don't really like grading that way. Okay, number 7. Point this camera back a little bit. This first K-map, so A, the most common issue on this was simply that people missed the wraparound square implicant. A lot of people missed it, did something more complicated, or circled only these two because they missed the wraparound. If you didn't do that, I think most of you got it right. B was overwhelmingly correct. It was a pretty straightforward K-map. There's 2 different ways to do it. As long as you picked one, you're fine. C was mostly correct. I'll skip that. You got the biggest issue on C is people added an extra implicant that it wasn't necessary, and I don't remember which one it was. But then D was the same thing. This one was supposed to be hard. This was the hardest of the K-maps by far. And if you look at my solution manual, it's kind of embarrassing the mistake that I made. So if you got a mistake on this one, don't feel too bad because I messed it up myself when I was trying to write the solution manual the first time. Okay, so here's what happened on this one. Most people went and said, let's find the big implicants, right? That works. And they saw this one, and then you might see this square, and then take the wraparound square. And here's where the mistake came in. You tried to circle the x's as though they were a big implicant. Now, what you'll notice from here, if I circle just these two ones, I'm done. I have to do that to get this minterm, right? There's no other minterm that I can pair that with. So this is an essential implicant. I'm done. I don't need to include those don't cares, right? Because I can pretend they're zeros and leave them out. So the mistake was adding this implicant. It's not adding anything to your cover, it's just adding those two x's. We don't care about those x's. Therefore, Miss Points was not quite the minimum expression. Now, the circuit still would work if you did that. It's just more complicated than you need. All right. Number 8 is kind of interesting because lots of you did it the way I did it and got the right answer. And some of you did it in different ways and still got the right answer. But there's one way that I'm not sure why it came up this way. And lots of people got it wrong doing that way. And I haven't puzzled it out yet, why they don't get the right answer. So the question is, let's take a 5-bit input and assert true when it's prime. So 5 bits means I need 2 K-maps. Let's see if we can. Yeah, that's better. Now, you have to decide on how to set up this K-map. What is your order? Now, an acceptable order would be, well, this is the way I do it. A, B, C, D, E equals 0, E equals 1. Now, the way that got people wrong is they counted this as 0, so minterm 0, and then this as 1. And then this is 2, this is 3, this is 4, this is 5. So all the evens ended up on this K-map and all the odds on that one. That ends up with a not minimal expression, or at least it did for everyone that did it. However, in at least 2 of the cases, I think there were 3 people that did it this way, 2 of the cases they made another mistake. So I need to go back and verify that they didn't do other things as well. Because if this doesn't, if you do this correctly, end up with a non-minimum expression, that's interesting. I actually haven't seen that before. So that is something that I have to take time and figure out why that you didn't get the correct answer if you did it this way. So if you do it this way, it's kind of silly. I'm gonna jump over here. Because the way you'd have to think about this K-map when it comes from the truth table is A, B, C, D as usual, but E hangs out front. Right? Kind of a weird way of writing out the truth table. Makes a lot more sense. I didn't write the truth table until after I did it, so that if I post the solutions, you'll kind of figure out why I did it this way. But this way, I just say, well, if E is 0, then it's 0, 1, 2, 3. Okay. These two, what I just about did was really common to flip. And that would get you the wrong answer. So 10 and 11 got flipped a lot, actually. So once I have that K-map and understanding of where these numbers are, I don't need the truth table, right? It's just fill in whether it's prime or not. And once you have that, most of these implicants are not hard, right? In fact, all but one of them are 2 terms is all. The only one that has more than 2 min terms in its implicant is the one that jumps layers. So you should have, when you end up with it, 6 total terms. 5 of them should have 4 variables, and 1 of them should have 3 variables. That's what I was looking for in the minimum expression. The benefit, if you have to do a 5 variable, doing it this way, putting the E out front, means your table looks like this. And then it makes it easier for me to grade you because I'll get the same thing as you do. It was a mistake, in my opinion, to not provide you guys with the K-maps. I'll not do that again if I remember. Okay, number 9. Okay, so this one was one of the major casualties of people that didn't read instructions. If you read all the instructions, it says design a pull-up network to complete the pull-down network below, then name the device. Start by creating a truth table for the circuit. Do all of those things. If you didn't write me a truth table for that circuit, you missed some points. If you didn't name the device, you missed some points. If you had no idea how to build the pull-up network, you should have still been able to see that it was an XOR gate, so you could name the device, and you should have been able to write the truth table for the circuit that I drew. You would have gotten 4 of 6 points, even if you had no idea how to finish the circuit, right? So directions, following them are good. Oh, I drew these weird, sorry. Okay. So what I wanted you to start off by doing is write the truth table for this circuit. Now, there's a couple different ways that you could have done this and got the right answer, or at least an answer I gave you points for. Because this circuit only tells you when it's 0. Right? Because if it's not 0, it's, I don't know, right? There's nothing pulling it up to 1. So if I get A and B, NMOS switches, this is beginning a few people. NMOS devices are switches in our class that close or make a connection when the gate or the input is a 1. So if A is 1 and B is 1, I've closed both switches and F is connected to ground. Okay. Similarly, if A is 0 and B is 0, both of these switches are closed and I get a 0. If I don't have either one of those, I end up with a circuit. I'll just quickly doodle switch style. That looks like this. So here's F. I have a closed switch here and a closed switch here. So I have a 0, 1, right? And neither one of the paths can pull F to 0. So you can either take the fact that you know that the pull up network is going to push you to a 1, and your goal is to just do the opposite of this. Or you could take it at face value and say, well, if it's 0, 0 or 1, 1, it's 0. Otherwise, I don't know or don't care, right? So that truth table or this truth table, either of those I give you points for. Because you know either way, right? So now your question becomes, how do I build? Well, let me get to the second part of this, the second point. What is that gate? Even if you only got this far, you have a strong implication that that looks like an XOR, right? And certainly that's an XOR. So as long as you did that table and then went, oh, that's an XOR, you got 4 points. In fact, a fair number of people did that and kind of like muddled through the circuit, got it wrong, but they still got a good healthy chunk of points on that question. So how do we design that circuit? My favorite way to do the pull up, and there are lots of different ways, is to simply write the expression that I want for the 1 and turn it into a pull up network. So F is equal to not A, B, or B, not A. Oh, sorry. Not A, B, or A, B not. There we go. Pull that out. So when designing these networks, and means series, right? A and B in order to get to 0 in this pull down. So and means series, or means it's a different path. There's a different way through it. Okay, so how do we do this? I'm going to jump over to this board. This says I'm going to have 2 transistors in series in 2 different paths. And it's pulled up, so it must be PMOS. Now, PMOS are trickier, right? They close or make a connection if the input is 0. So that gets confusing. Now, there's two ways that you can deal with this. One is you could explicitly draw out an inverter to help you kind of think about what that means to undo it. Or you could write the inverse term. So I'll do both ways. I'll do one way on the left and one way on the right. Okay, so first one, A, not A and B. Okay, so if I put not A in here and I invert it, I get, so that would be a 0, that is a 1. Ones don't close that, right? Zeros close that. But that's okay. And I did something nice for you guys because I know that this is tricky. It turns out it doesn't matter how you do this, because if you just wrote not AB and AB not, so, well, I'll finish off this way. So A bar B, and then here, the other way of doing it, instead of explicitly drawing out the inverter, would be to draw bars over both of them. And then I would end up with the right circuit. But this circuit is mirrored. So if you didn't think about the inversion and the fact that PMOS is flipped from NMOS, and you went, okay, well, this is A bar B, and this is A B bar. Well, you got the right answer for the wrong reasons, actually, right? Because this, A not B, is true when A B bar. So the fact that they're flipped meant it was really difficult to mess that up. So there is another way of doing this that some people did, totally fine, is you can write the expression for the zeros and use De Morgan's. That's perfectly fine. I don't remember the circuit, I didn't draw it down, but it ends up looking something like, I think that. So if I have, well, let's think about it. If I have 0, 0, 0, 0, that closes and pulls up. Okay, so that's not it, right? Because a 0 closes that switch, a 0 closes that switch, and current is flowing. I'll grab a different color. There. And because it's 0, 0, we're also connected to ground. So instead of flowing to F, it flows straight to ground. We have infinite current flowing, right? Because we're connected straight from power to ground and everything blows up and breaks. I'd have to go back and think about what there is another form that is valid, but I don't recall what it is right now.
The B and the B not just need to be switched.
Oh, the B and the B not need to be switched. That makes sense. Let's check that one then. Okay, so if I have 0, 0, this is closed and this is closed, but neither one of these are open. So it's broken. Same case in 1, 1, it breaks here instead of here. Right? So perfectly valid circuit, multiple ways to get the answer. As long as you guys did it, I didn't mark you down. If you think you found a third way of doing it, and I marked you down for it, come talk to me, but I would be very shocked doing this circuit. Okay, so that's that one. Number 10. Is VHDL case sensitive? No. I said that a whole bunch in class. You can go check it online with a simple, is VHDL case sensitive, right? Part B, write 2 lines of VHDL to make a full adder. And later it says, use XOR gates where possible. Now, the 2 mistakes that I saw most prominently on this one is, one, they didn't write 2 lines of code to represent the full adder. They wrote the declaration or instantiation instead of the full adder equations. And the other one is, instead of writing XOR, they used the symbol, which is not correct. I'm not sure that most of us know how to type that on a keyboard, and I'm certain VHDL doesn't know how to compile that symbol. So those were the 2 mistakes that I really saw, or they just didn't use XOR gates, right? Because you can write the sum expression without using XOR, but I said use XOR gates where possible. I still gave you some points if you did that, because you had the right idea, but it wasn't the full expression. C, hopefully you all know now, it's asking, do you use multiple component declarations or multiple instantiations when you're using more than one of a component? Well, you just use one declaration. You say this component exists, and then you use multiple instantiations, say you use it multiple times. Everyone that's completed the lab on Monday is probably pretty clear on that now, right? And on Thursday, I'm going to do another example in VHDL so that we get really comfortable, because we're making the transition here from building hand circuits into building everything in VHDL. So that's the direction we're going. And I want to make sure that everybody is nice and comfortable using VHDL. It's all been pretty easy for now. It's about to get interesting. Okay, number 11. Actually, I almost made a mistake on this one. Lots of you almost did the same thing, which is the flaw of didn't read the instructions completely. It says to draw and use a K-map to provide the minimum product of sum expression. Lots of people did the sum of products. It's not the right answer. The only other issue, if you got the product of sum right, which means circle the zeros, right? Then some people missed the, I'll just draw it rather than using words. In the K-map, there were zeros here. And students got that one. Everyone got that one. But some people made this orange circle instead of this black circle. Right. And what that's going to do to you is you're going to end up with one of your terms has one too many variables in it, because your implicant was insufficiently large. That was a major mistake on this one. Other than that, everybody got it right. I didn't dock you points on part B. If you did that wrong, I didn't cascade your errors. So as long as your part B circuit matched the equation that you resulted with on 11, you were fine. Even if you wrote a sum of products expression instead. If you wrote the sum of products expression, part C got pretty hard though, right? Because part C is asking you to convert the circuit to NOR gates. So if you did the sum of product expression, you did the product of sum expression, then you ended up with an AND gate with many inputs. And then when you need to do the conversion to NOR gates, it's just that simple bubble pushing, right? Where I add bubbles to those, and I'm done. People miss points because they didn't read the next part. You need to use NOR gates as inverters to have the inverted variables. Again, just didn't read it all. What that meant is one of two ways. Well, there's actually like three ways, but you could have then if you had A and then you needed A bar here, what you would have done is say A goes into here, I invert and do less, not quite right, because I said use NOR gates. Well, I could either draw the NOR gate as this, right? That's an inverted NOR gate. Or if I remember correctly, because I don't usually do it this way, so I may make a mistake, but I think it also works this way as well. Either one of those case. And you could either draw those in this circuit, like that, or you could just say this equals that, and then kept writing inverters. Either was okay. As long as you showed me that you knew how to turn an inverter into a NOR gate, you're fine. Well, NOR gate into an inverter, you were fine. Part D, only a couple of points. What would you do differently at step A to make it most simple to create a NAND gate? Most simple, right? Well, the mistake here was you didn't read the instructions again at step A. So there are other ways to do this. But step A was draw and use a K-map to make this equation, right? Well, the way that you make NAND gates easy instead of NOR gates easy is you do sum of product instead of product of sums, right? Because it's just, again, bubble pushing. That is the most simple way to do that conversion. Last page. I'm really curious on this one, how many people didn't have time and how many people just didn't look at the last page? Because this was far and away the most missed points of anyone, I think, is just not doing problem 12. So, something I noticed after I handed out the exam was that I didn't tell you you couldn't use a K-map. So I did tell you you couldn't use a Boolean algebra solver, and that was true. It would be a very confused if you tried to go online and do that. But the K-map is fine. And in fact, even if I said do the solution without a K-map, you could do the solution on the side of the K-map to make sure that what the answer was supposed to be, and then gone back and figure out the algebra. But if you skipped straight to the K-map, you got full points because I didn't say don't do it, right? So another case of read the instructions carefully. The first one, when you turn it into a K-map, you really quickly see that, right? And if you do those expressions, you find that the third term, A and C, is redundant, right? So you can just throw that out. So instead of the original expression is this, turns out this is completely unnecessary. You can find that through expansion, or you can find it through the K-map. Either was acceptable. Now, I did put this note. You may want to do this problem last if you have a difficulty with expanding algebraic terms for simplification. Most of you listened to that and did it last, it looks like, and that's good, because the very last problem was a trick question. It was already in its most simple form. Yes. Now, if you did the K-map, it was super obvious that it was the most simple form. If you didn't do the K-map, it was a time sink. But that's why I said do it last, right? It's only worth 3 points. It's not that many. And I just wanted to make sure that you guys could think about it and go, okay, this is weird, but it's all fine. That's all that question was testing. I want you to think about that. And as you go through, when I ask you to do things, if you know a different way, that's easier for you, go ahead and do it, get the answer, and then try and solve it the way I asked, right? The reason I do this, ask you specific methods, is because there are times when they're more useful. Different methods are more useful at different times, so I wanna make sure you know all of them instead of leaning on just one as a crutch. But if it's an exam and you want that crutch, by all means, use it, right? Do we have any questions on the exam that I didn't address? Okay. I'm gonna go ahead and collect those then so I can get the scores entered into Canvas. No, I don't care. Okay. Oh, you can come at me after class and pick it up, but I want to hold on to it. Oh, did you do it online? No, you didn't. So yeah, if you guys have questions that you want to ask specifically about your exam that you don't want to ask in front of the class, find me during office hours. I just don't want to leave these out floating around until I get them entered in. Okay. Now what I want to do, let's see, how much time do I have? A little bit of time. What I want to do is I want to bounce around to some people and just ask and address where you're most confused. I'll get to as many people as I can because I want that sampling to understand where I need to focus that extra help. If anyone has a point of confusion that they'd like me to start at, you can go ahead and volunteer. Otherwise, I'm just going to start calling on people. Any volunteers? Nope, you're all super confident. All right, what is your most confusing part of this class?
It was the HDL, but after the lab last night, I kind of cleared a lot of it up.
Great, perfect. Yeah, and we'll get even better at that as we go along. What's your most confusing point?
I didn't study the number conversions enough. I think I wasted a lot of time on that.
Okay, yeah, and remember that you can always do a calculator to get the answer and then go back and make sure that you did it right. Verify your answer. The more prepared you are. I like doing these kind of time crunch exams because I don't have to worry about people cheating as much. Because like last semester, someone tried, and two people tried, and they posted answers to Chegg or questions to Chegg, and they didn't even get the answer in time, and then they failed the class because they failed the exam for cheating. But the trade-off is if you're prepared, if you study, and I try and make my study guides pretty obvious. Did you guys feel that the study preparation was okay, sufficient, or did I need to do better? I did okay? Yeah, so I like to make sure that there's not huge surprises. Sometimes they'll be complicated and hard, but most of the time I just want to test that you understood what I talked about. So yeah, what you've discovered is if you prepare the right things, it's usually kind of just breeze through it, and then you can go back and check. If you aren't prepared, it can be hard to double check. What's your confusion?
That's what he was saying, VHDL, but I was cleared up a bit yesterday, and then some of the stuff we went over last time, like decoders and read-only, but when we do homework, though.
Absolutely, yeah, we'll get to more to the decoders there. The point with the decoders and encoders is that students always struggle with these. They're always hard. And so what I've done is I've introduced them 2 weeks earlier than I normally would have, and then I'm going to give us lots of time to build up and understand them. So there's no rush on those of VHDL, because I also introduced VHDL a month earlier than I did last semester. Jason, what's your confusion?
I think everything from the last 2 weeks really has been the most confusing for me.
Okay, pick one for me. Let me know that the worst is.
The NMOS and the PMOS.
Yes.
Those ones have been the most confusing for me, I think, so far.
Okay. So if you can get good at everything else, if you can get comfortable with everything else, right? If you can get to the point where one weak spot, you're in good shape because you can spend a little more time thinking about it. Because let's look at that first circuit on the exam. And if you had some more time to think about it, you can redraw this circuit every time, understanding that the NMOS, if it has a 0 here, is equal to an open switch, where this is A and this is B, A, B. And for PMOS, if this is a 0, you get a closed switch. So for each case of, sorry, it's A and B or not A, not B, you can redraw the circuit and take your time and say, what does that circuit look like when I get 0, 0? What does it look like when I get 0, 1, etc.? Well, let's draw the circuit when I get 0, 0. Zero means open. 0 for B also means open. Well, on the other side, if I have 0 as A, then not A is 1. And a 1 closes an NMOS. Same thing, if B is 0, then not B is 1. A 1 closes the NMOS. There's the circuit for 0, 0. If I were to go through then and say what happens in the case of 0, 1, I'd find this. And you'll find that there's no way for me to draw a path from F to ground. So it can't make a 0. So it's just kind of hanging out. And you don't want, unless I tell you guys, to have undefined outputs, so that the pull-up network is just going to do the opposite. Now, you can get confused really quickly in this class if you were to go and start Googling behaviors of NMOS transistors, because these devices are actually way more complicated than just a switch. And that's outside the scope of this class because that's analog behavior of circuits. We're interested in this digital behavior of circuits, where the only thing we can apply is on or off, right? In an analog circuit, I can go in yes. So in an analog circuit, this is the kind of common circuit that you would see. And what this does, if we're digital, right, is either makes it 0 or open, right? Because if it's open, I get pulled up through this, what we'll call RPU, R pull up, right? So if we're 0 or off, we're not connected to ground, it gets pulled up to VCC. This is how we build our switches, really, right? But instead of using NMOS devices in our lab, we're just using actual physical switches. But it turns out in an analog circuit, and this is what you could run into if you were to Google it, you could get yourself confused, is it turns out that this is what we call an amplifier, where it's going to take the input signal and put an output signal that is bigger here, that is actually multiplied by the size of the resistor. Now, you'll cover that in later classes, but be aware that if you see that doing weird things, complicated equations, it's coming from analog circuits, not digital. Digital is easy. We like digital circuits because they're simple and they're just on or off. Now, they stop being on or off necessarily when you get to really advanced technologies, but that's like master's and PhD level stuff, so you can pretend it doesn't exist. I'll move on to the next. And if you have, any of you, as we go through this sticking point, I want you to use my office hours. I mean, I don't mind sitting out, hanging out my office hours and chatting with the other professors. But even if you see me talking with like Dr. Gibbons and something and it's office hours, I will stop socializing to do my job, right? Part of my job is mentoring you guys if you're confused. I can only do that if I know you're confused. That's kind of why I'm doing this today, is to see where we're kind of sitting. Okay, where are you most confused?
It was the same thing you was confused with.
Okay, does this help?
Yeah.
Okay. Where are you most confused?
I think I'd probably have to say when you, I guess, I don't know, this is more recent to logical devices when you were like connecting muxes together. That was probably confusing me, or, I mean, there's a 6 variable K map. I'm still kind of confused on that, but I don't know how important it is to go over that.
The 6 variables, not super important. I want you to know they exist. I didn't put it on an exam. I'm highly unlikely to put it on the final. So if you push that to the back, but if you want to know, I'll use my office hours, I'll cover that. But the other concept is really important, which is cascading devices to make bigger devices, right? And the muxes are the same idea as the OR gates. What happens if I only have a 2-input OR gate, right? Say you're in lab and I'm not there and you're trying to build a circuit. And all you have is a little circuit that has a bunch of 2-input OR gates, but you need a 4-input OR gate. How do you build it?
You would connect the 2 OR gates into the bigger one, right? Or into another one, sorry.
Yes, exactly. And you can prove this to yourself really easy, right? So if I called this X, this Y, and the output Z, then X is equal to A or B, and Y is equal to C or D, which means that Z is equal to X or Y, which is equal to A or B or C or D. And because of our properties, that's the same as a 4-input OR gate, right? Well, the muxes do the same thing. The muxes just get confusing because they don't have the simple logic operation of OR. They have a select signal. Actually, we'll call this S1. So, in order to allow this circuit to select which one it wants, of A or B, based on select, we need to be able to provide A or B to it, right? So if S1 is a 0, then I output an A here. So 0 makes an A. And down here, a 0 makes a C. So now with S0, the other select bit, I get to choose A or C. So 0, 0 is A, and 0, 1 is C. Right? And I can go through and cascade that up to really large numbers. Now, this is not necessarily super important right now for you to understand immediately. The idea of muxes, this idea of selecting and taking the inputs at the output is going to be very important. Because what we're going to build up to, and I do want to kind of sneak this towards you guys, is we're going to be building a processor. And what a processor needs to know is, what operation do I do? So I'm going to have some output F that the processor is going to do something with. Well, inside of the brains of the circuit, I'm going to build, say, an adder, a subtractor, and a multiplier, right? Well, this is this concept of hierarchical design. where this is gonna be like your CPU, your processor, your top file, right? Well, in lab, we built this adder. You suspect that maybe we're gonna build maybe a subtractor later and maybe some other things as we go along. And then we're gonna start piling them into a processor. Well, how do we get the output of adder? Processor is going to send a command that says, I want you to do an operation for me. I want you to add. Well, how do we choose add? Well, we could have enable signals on all of these and doing a bunch of stuff, or we use a mux that takes the command and just plugs into the mux. And if my command is add 0, 0, the mux says, I'll just take the output of the adder. And if the command is subtract 0, 1, I'll take the output subtractor. Yes.
And the reason why we have to chain a bunch of muxes together is because each signal, each bit can only be 1 or 0. And so you have to chain up multiple of them to select through more than 2.
Yes, exactly. And if you want, it gets easy to build large muxes. You're going to design a 1-bit mux. If you understand that connection, you'll never have to design another mux. You'll just connect those 2-bit muxes together in that cascade.
Okay, so how would a 3-input mux work like that one?
You would actually need to make a 4-bit
Oh, so yeah.
and have an unconnected bit. Because muxes are always going to be a 2 to the n. In fact, almost everything in digital is 2 to the n of something.
Okay.
We got still some time left. Where's your confusion?
I just need to read instructions.
Good skill.
Probably, and just like the HDL, but like the lab cleared that up. And of course,
Great, yeah, and we'll do another one Thursday for everyone that's kind of on the fence with VHDL. It's kind of like a silly example, but I think it really elucidates the issues.
I'd say VHDL as well, and then also for these transistor switch, like the one you have over there.
Yes.
So I'm kind of confused on pull up and pull down still.
Okay.
So if there is a line connected from power to the out, that means it is 1. But if there's
Yeah, from
not-
power to out, it's 1. From ground to out, it's 0. Yes.
Okay, so that's where I got confused, because I thought it from there to ground would also be 1 because you're connecting the circuit. But you're
Yeah, unfortunately not, because what creates a voltage or a 1 is resistance. If we don't have resistance, we go power to ground, it turns out ground wins, right? I mean, think of it as like lightning, where the sky is 1 and the ground is 0. The lightning strikes and it has enough heat and power to turn sand into glass, but it still just disappears into the earth like nothing happened most of the time, right? Ground wins. We can't create enough electricity to create a voltage when you're connected to ground. So yeah, you'll see it in your circuits too. If you ever connect power directly to ground, it'll go to 0. It'll just give up. It's like, I can't do that.
Okay, so if I want to make it, so if it's going down, if it's connected, it's 0 because it just goes straight to ground, it doesn't care about anything else.
Technically, it's on fire.
Oh, okay, okay.
Because these devices do have a little bit of resistance in them. And if you connect them power to ground using them as a switch, their maximum current gets exceeded. They get really, really hot and melt your plastic and hopefully don't light something on fire, but they
That's how you let out magic smoke.
Yes, yes, magic smoke is a term that you'll come across in like DIY forums.
Okay. All right.
And we do have a question left for you. You can get all the way through, Zach.
I'm good.
You're good. Yeah. All right. That's fair. So anyways, I want to iterate again. You guys did very well. I'm very happy. That was a hard exam and you guys did great. So thanks for your time. If you have questions, reach out to me via email or office hours. I'm happy to help clarify. We're about to get into some really interesting stuff next week. Have a good day, guys.
Yeah,